This is the first lecture on really robotics in the technical sense. This opens the sequence on vehicle motion generation, motion planning. I'll begin by first stating that problem a little bit, and then I'll essentially introduce in this single lecture the entire attractor dynamics approach. So it takes a little longer than a regular lecture. It takes a little bit over time, but as you know, we're skipping 2 lectures because we have these holidays and so on. So it should be okay. Good. So attractor dynamics approach to vehicle motion generation. So what is the problem that we're looking at there? So it's generating movement of a vehicle. The world is 2-dimensional for a vehicle, right? It's a plane. We're talking actually indoors here. In outdoors, you have elevation, but in terms of control, it is working within a surface. And the kinds of constraints we'll be looking at is moving toward targets and avoiding collisions as you're doing that. That's the core problem of motion planning for vehicles. Motion planning for arms is analogous. You're trying to reach a particular configuration and you're trying to avoid obstacles. It's not totally unlike, but it's higher dimensional because the arm is a more complex object. There could be other constraints. The most typical constraint that you find in autonomous cars is to stay on a certain road, right? You have constraints like how you maneuver. Actually, not a trivial problem. For instance, when you avoid an obstacle, you have to take into account that you want to stay in your lane or stay on the road rather than plan a avoidance path that goes off the road. In some contexts, there's also another constraint, docking, that is to be in a particular orientation. I'll actually say something about that in a moment. I'll not treat that. We actually did treat docking behavior in the past. And there are other kinds of constraints one can think of. And so what are the degrees of freedom in this kind of context? I'll define degrees of freedom more formally toward the end in the lectures about arms, where this is a much more complex problem. So ultimately, what we're talking about for a vehicle is how many different ways can the vehicle be configured in the world, right? And then there are 3 ways it can be configured. There is its position in 2D, that's its location in the world, and its orientation. The vehicles have some forward direction, and that's 1 degree of freedom. So there are 3 numbers there that characterize the state of the vehicle. Often the orientation is not intuitively immediately obvious, but of course it is a degree of freedom. And the vehicles have this particular property that's called, in a technical sense, non-holonomic constraints, that there are fewer variables that are really freely choosable than degrees of freedom. And so in vehicles, it's very obvious. If you know cars, then you know that you really only have steering. Right? Steering is 1 degree of freedom. That's just one angle of the steering wheel, and you have the gas pedal, right? That's the speed you control. So it's only 2 variables, but you can achieve position and orientation of the vehicle. These kind of constraints are called non-holonomic. We don't need to, there's a whole mathematical treatment of these sort of things in general. The kind of vehicles we'll often consider are have active wheels. So often we look at these as these circles in my naive drawings, meaning that under these two circles there are active motors. I showed you some robots last week in the introductory lecture, and many of those were of this kind. So they can essentially have 2 variables, the speeds of the 2 motors. Everything else is passive. They might have some caster wheel to keep it from falling over. And so the 2 variables are the 2 speeds, essentially the 2 motors, also 2 variables. And you can see that determines both how fast they go. The average speed of the 2 wheels determines how fast they go. And the difference in speed determines how much they turn. So non-holonomic boundary conditions are actually a little bit, form some kind of mathematical challenge. And I will actually pretty much avoid that in this lecture because it's not really about the technical side so much as more the conceptual side of this. So in these kind of vehicles, we'll often look at these vehicles that have active motors. It's not a real problem because you can freely choose your orientation by rotating on the spot. Once you drive to a spot and just make a movement of the wheels that have average 0, so one goes as much to the left as the other to the right, then you can turn on the spot. As many of you who have a driver's license know, that's not the case in cars, right? In cars, you have to do some complicated maneuver, like when you park. And that's where you see that the problem is that the relationship between the degrees of freedom and these freely variable, choosable variables is history dependent, right? If in parking, you might be aware that if you got yourself into a difficult situation, it's difficult to get out of it. And there are theoretical cases where you cannot leave your parking spot, for instance. There's actually a lot of work on autonomous parking, on autonomous, leaving your parking spot. And these algorithms are much better than humans are. But there's a problem, for instance, if you, as a human, you leave the parking spot that your car autonomously parked into, you mustn't be able to get out of it because it can park so optimally that it might be hard for a human to actually do that. And typically, currently, it's not changed. Currently, it's the human who has to do the deparking because you're entering traffic. While when you park, you're leaving traffic. Anyways, that's a side aspect. So I will not go more deeply into these aspects. I will consider here really these vehicles that have only 2 variables. In fact, most of the time we'll only talk about 1 variable, the steering variable. And so what is entailed now in generating movement for vehicles? The main issue is you have an environment, right? If you have a plane that's totally empty, like in a computer game, you can move in any direction ahead. It's arbitrary, you can do anything. So the main constraints come from there being stuff in the world. So maybe you need to know where your target is and where obstacles are. And if you have these other constraints, maybe where the roads are and things like that. And so based on that kind of information, what we consider planning is generating trajectories of your degrees of freedom, so time courses that are collision-free and achieve the constraint, for example, go to a target, for instance, or stay on the road. It's then a separate issue that to actually physically bring that about. That's what we call control. Now you have your plan, and you bring that about in the vehicle. Classically, that's considered a totally separate topic that has different mathematical constraints or different concepts. And I will be talking about that a little bit in the lectures about controlling robotic arms. In vehicles, that kind of control tends to be a little bit simpler, even though, for instance, for cars, when you deal with control, you have to deal with physical disturbances, right? Our lab robots are very simple that way. They work on very smooth surfaces and they are not very good in dealing with physical disturbances. But when you drive on the road, of course, you have a lot of complex design features that make your car stable on the road, and there are active stabilization systems and so on. Okay, so in vehicles, I will not really talk about that. The other problem that is related is that once you have acted, change your physical state in the world, you may need to know that, to estimate where you are now. That is actually what the problem of navigation, knowing where you are relative to your sensor information or your map. And I will have a little lecture about that in a couple of weeks. That will be the last lecture about vehicles, about equal position estimations, what that's called. So for now, you will see we'll kind of trivialize that. We'll trivialize that because we will be assuming that we have sensor information about where we are, that informs us about where we are in the world. I'll go into more detail when we test that. So that's sort of the minimum that you need to do to generate behavior. And I will be now talking about planning. I'll not use that word planning a lot. I'll talk about generating movements. And you'll see in a little while that in some of the approaches, it feels more like control, like you're doing this online, changing your mind every moment in time. But it would actually be what in robotics is called planning. When you talk about planning, people think usually like a whole plan that you have already fixed and then you act it out. But you can have a plan, it's sometimes called online updating, where every moment in time you update your plan. Then it feels more like control, but it's actually conceptually really plan. Good. And this distance difference I already hinted at, different kinds of planning. actually is expressed in robotics in terms of different architectures. So these are the two limit cases. There are a lot of intermediate different variants of that. One extreme is the classical sense plan act architecture, illustrated on the right. The other one is sometimes called behavior-based robotics. And again, there are many variants of this. So in the sense plan act architecture, you have a special level at which you do the planning. And the planning is based on a model of the environment that includes also your own, the configuration of your own vehicle. That representation or map, that model of the world, could be informed by sensor information that you have, but it could also be informed by offline knowledge. You use GPS, you're using some sensor information related to the satellites to know where you are, but then you fill in all the information that's in the database about where things are in the world once you know where you are. And so all of that is sort of localized in the architecture, and then the planning builds on that, and then goes to the acting would be the control. So that's sort of classic in that sense. That was the original conception of how you would think of autonomous systems in very general terms. And artificial intelligence still very much is based on this kind of idea. Artificial intelligence, you would have all the intelligence here in these two modules. So this would be conventional, sensory processing, and this would be conventional control, and all the intelligence in how you do these maps and how you do something intelligent, plan something intelligent. It could be more than just vehicle pathway. Does the noise bother anyone? No. If not, just feel free to close the window. So the reason why people even thought about an alternative to that and are still using actually quite a lot of this alternative is that this makes a lot of demands on perception. This sort of to build the world model is hard. It actually was the major bottleneck for a very long time. In my introductory lecture, I talked about perception. Perception is one component of that. Is going from sensor information to some estimation of what object is where, in which pose, what its boundaries are, and so on. That turns out to be a very, very difficult problem. It's a problem that organisms are particularly good at, and that our artificial systems are still not very good at. Even these famous deep learning algorithms don't actually really solve perceptual problems in this full sense. And again, that would take a whole lecture to sort that out, but I could just claim that. And so people were thinking, is it possible? So the crisis in this field was sort of in the 80s, after maybe already 20 years or more of efforts toward autonomous robots. The robots weren't really doing anything. They had a vehicle, a famous Stanford cart, that would take 15 minutes to reflect, and then it would make one little move, and then had to do a lot of computation. Of course, computers were also much slower and had less capacity, but it reflected the underlying problem of generating these maps. And so the one alternative was this, what is called behavior-based robotics. This was made famous by Rodney Brooks, who's sort of a household name, perhaps, I don't know. He's also a co-founder of that iRobot company that makes these vacuum cleaners. And he's done this sort of, I think it's called Heartland Robotic Company. And he's a famous guy. If you don't, he has a very interesting blog. Just you can just Google his name. It's really interesting. There's a complicated history of this, but he's sort of the main proponent of that. He proposed a particular variant that was called the subsumption architecture, and I'm making a simplified caricature of that. And in that concept, you would say any kind of constraint for my planning, the kind of thing I want to achieve, needs only specific information just about that. I don't need a general world map. I just need some central information for that particular behavior. So for instance, if I want to avoid obstacles, maybe I only need some sensory information about free space, or just some depth map. Don't need to know about objects and obstacles. Anything that is close is an obstacle. So you don't even need to say it's different obstacles. You just need to know what's my depth profile, and directions where there is a lot of depth are free. That's where I can go. Right? And so you could say for obstacle avoidance, I will have specific sensor information, and maybe I also have to only control only certain things. In the simplest way, maybe I just control speed. I just stop when there is something blocking my way. Right? That will be a very simple algorithm. And that is with something they call a behavior. So each behavior has its own loop from sensor information, whatever the algorithm is, to the control variable that is sent down to the motor system. If you could have other behaviors that, like maybe targets might require slightly different sensor information. Maybe target really requires detecting an object, or at least some feature of an object. For instance, they famously built a robot, Coca-Cola can robot. So it would always try to find Coca-Cola cans, Coca-Cola, because they are red, right? And they just used very simple vision. I mean, anything that was red was a potential target, and they would essentially detect blobs of red, and then they would just control the robot to move such that the red blob becomes larger on the retina, on the camera plane. And that meant the robot was approaching the Coca-Cola can. And apparently it worked a little bit for a little while. It was very crude kind of demo. This was the sort of idea to have minimalist architectures that achieve something in the world. And so that the sensor information for this part would be different than for other behaviors, and maybe also generates different outcomes. In fact, the strength of this approach comes from this what's called subsumption, the idea that these behaviors could interact. So, for instance, one behavior could provide input to another behavior, or the output, no, and the other way around, the output of a behavior could be the sensory information for one behavior. And I will essentially show this attractor dynamics approach that I'll go into more deeply overlaps with both of these. It can be used in this style, but it can also be used in this style. So we get a more concrete sense of what this actually means. Good. And some other concepts that allow you to localize what I will be teaching now are four more concepts I'll explain. So after we come through the attractor dynamics approach, we'll have a lecture about other approaches, and then I'll sort of sample these spaces. But I wanted, unlike in the past, this time I really wanted to make you aware where we are in this landscape right away. See if that's pedagogically better. So another distinction is global versus local planning. So global planning is essentially when you already know the entire map, and you're able to use that to plan in a way that takes into account that you're not going into a dead-end road, for instance. So if you know the plan in a building, for instance, you might want to be aware where if there are doors or if there's a wall you can't go through, and that would be typical feature of global planning, that you don't choose a route that doesn't work, and that you find the route that works. And there's a lot of mathematical work on doing that. While local planning would be planning that is only using the information that is directly available to the sensors, or if you have a map that from the vehicle position of point of view, you can read off the map, like distance and so on, and you're only to that sort. And that's closely related to reactive versus sometimes called deliberate planning. Here, just called planning. So yes, please.
So planning essentially without planning without history, the road, opposed to global, where using, for example, SLAM, I essentially keep in mind, speaking for the robot, the entire environment I have already discovered.
Yes, so SLAM would be the particular case. I'll talk about that in the navigation lecture. The case where you have a map that you acquired yourself, and so that map could contain non-local information, that is, could contain information about objects, obstacles, maybe blockages and so on, that are not available to your sensors right now, maybe occluded, falling off, and so on. And so if you have a map that resulted from SLAM, you could do global planning. That is, you could choose, for instance, if you have a choice between two ways to avoid barriers, you could choose the one that will lead you to your target later on, when you're further along the path. That would be a global plan. I don't think I fully understand what you mean by history.
Because you said that the local aspect is with regards only to the information the sensors have right now.
Yes.
So if I start keeping a record, which essentially SLAM super simplified is for any method would be.
Yeah.
Then so as soon as I start keeping a history of information, I'm moving into the global.
Yeah, so very interesting question. Good. For the online folks, maybe I should repeat that. So it's a question of using your history of sensory information and maybe your control history. Does that then lead toward global planning? And I would say, these are just concepts. So it might be a question of in each individual case how you do that. You can use history, but without doing global planning. So it's not logically the same. So for instance, and I'll actually talk a little bit about that in my other approaches lecture. If you have a sensor that is not very reliable, the classical example was sonars. Sonar sensors give you distance information, but only if the object has the right angle to you to reflect the sound wave. And so when you are in an environment, you will get a sonar signal when you are sometimes, but not at other moments in time. And using the history of signals that you got, you can build a map, but that's a map only of kind of surfaces that would be local, because you don't get anything about what's behind that wall. You only get that when you drive around that wall. So you would be accumulating history information just to make the sensor information more stable, to essentially something like a Kalman filter or probabilistic approach. But you could still do purely local planning, which is actually routinely done with these kind of systems. When you do global planning, that requires more. That requires, you were hinting at SLAM, and I'll talk about SLAM later. That is, that you then also need to know where you are in that history. Relative to that history, you have to estimate your ego position, and that is actually also a problem. This is also pretty much solved, I would say, but it's a problem. So conceptually, it's not the same. Conceptually, you can do local planning and use history just to stabilize the sensor information that you have, like a Kalman filter. Good. So related concept is this reactive versus planning. And reactive is essentially this idea that I was hinting at, that you could be planning on the fly. That is, you take your current sensor information and always update your plan. And so in that sense, as autocracy, that requires local. It's very difficult to do that with global. While real planning would be something where you're where the plan has some extension in time, and you might be able to update it, but you plan a longer sequence. It doesn't have to be based on global information, it could be based on local information. For instance, even a docking behavior requires that. Docking behavior could be something like your robot vacuum cleaner docks. If to go to the power station, it has to drive to a particular position, but also be oriented so that it contacts the battery. And that will be done by approaching the docking station, you can imagine, to a little bit in the right angle, so it can actually do that correctly. It can't rotate on the spot sometimes because of the mechanics of the docking station. And that requires some real planning, because you have to sort of plan to go a little bit out and then come in. You can observe that if you have a vacuum cleaner of that kind. But it's still based on local information that is on everything that is within sight of the robot. Many of these don't have global plan. The only one that I know has that is the Dyson, which is much more expensive. That makes a real map. That actually does a SLAM. I'm very interested. The downside is it's a bit higher and it doesn't go under the sofa, so not so popular. Good. Okay, so that's these two concepts, and then exact versus heuristic. So that's heuristic really just means that you have an approach with some some heuristic and assumptions, and so it will often work, but it is not guaranteed to work. For instance, it's not guaranteed to find the path if there's a path, or if you have constraints, then it will very often avoid the obstacle, but there is no 100% proof that will avoid any obstacle. And of course, almost all approaches are in that sense heuristic, but there is a whole business of having exact approaches. That is, you have a mathematical formalization of what that information of the world is, and then you mathematically prove that with a certain algorithm, you will always satisfy all the constraints. And there's a whole industry is now maybe no longer so active, but certainly still active in the ARM planning. Turns out very interesting mathematical problems arise, and there's a whole industry of trying to develop algorithms that are exact in that sense. So for instance, they would represent the world in 2D as a set of polygons, so sort of piecewise linear walls, and then prove that for under certain circumstances, certain algorithms always find a path if there is one that fulfills constraints. For instance, even taking into account that your obstacle has your robot is not a point, right? It's an object that is a line. You have to imagine it gets complicated real quick. If you have some complicated rectangle and some corridors, does it fit through? Can it turn? You see that it will be interesting problems. Good. And so the attractor dynamics approach is a local, reactive, heuristic, and continuous approach. Oh, the last I forgot. So you have continuous approaches that are space-time continuous, and then there are discrete approaches, for instance, that work on a grid or on graphs in general. For instance, reinforcement learning, many of you might know, discretize the states because they make search and continuous space. That's a little bit difficult. So we're talking about the local, reactive, heuristic, and continuous approach, right? And later I'll show you other variants. I'll not show all of those in these lectures because that takes a whole course to go through all of these. And so we're actually the inventors. As my students in Marseille developed this approach, and we had a couple of collaborations. And it turns out there are a couple of other researchers who did something similar. There's a relationship to the potential field approach, which I'll be reviewing, but it's not exactly the same. And so that's somewhat original thing. So it's just so you know, it's not an approach that 100,000 people are using. And I developed that as the idea that would be consistent with certain principles that we developed to describe how nervous systems generate behavior. So there's sort of a neural inspiration, even though the approach is not really concretely neural. It's not like there are neural networks in there. Those who listen to my winter semester course know about neurodynamics and stability, bifurcation, and so on. And so it's using these kind of mathematical concepts. It actually turns out that the approach does really model human behavior, but that was actually discovered only after we developed it. So it's just conceptually motivated by using these ideas of stability and bifurcations. And then it turned out it actually describes human behavior quite well. And in the navigation lecture, I'll show you that the variables we're using, heading direction, are also biologically quite plausible. And there's some real analogy. And in a sense, it's lucky. I mean, it didn't really have to be that way, but maybe that reveals that if you add constraints that I will be discussing now of stability and so on, then there aren't 15,000 ways how you can do that. So that's why we really discovered that. So there are two variants of the attractor dynamics approach. We call those symbolic versus subsymbolic, which is a little odd way we thought about it. It would be better maybe to call one to be the sense plan act version and the other is the behavior-based version. I'll begin with the symbolic, the sense plan act version. You will not even notice that initially, but then when we go to that one, you see the difference. Okay, so what is it? Here are the basic ideas, and I will expand on those now in a couple of slides. So basic ideas is that movement plans for vehicles are time courses of behavioral variables. We will actually only discuss one here, heading direction. These time courses will be generated by a dynamic system, a differential equation, which we built. The equation is built and designed by us so that its attractor solutions generate these time courses. I'll have to talk about how an attractor solution can generate a time course, because so far from the lecture that Lucas gave you last week, you might think that these are mostly fixed point attractors. And no, we'll see how that works. And then bifurcations of these attractors, so instabilities of the attractors, will make these systems capable of decisions. You remember from my introduction, we say that a autonomous system is an autonomous robot if it can do some kind of decision making. It's not just a regulator or control device. Okay, so I'll unpack this now as I go through this. So let's be very concrete about that. This can be generalized, and we actually wrote a couple of papers about that. But I'll just talk about the simple vehicle path planning example as the one that we make specific. So we use this term behavioral variable that comes from the biological motivation we had originally. It's just in all the papers, so I'm still using that term, but it's really the variable in terms of which the plans are formulated. And so the behavioral variable that I'll be discussing here is the heading direction of the vehicle, Fahrtrichtung in German, right? The second variable would be typically the forward speed of the vehicle. And of course, when we design these robots, we always have that variable, but I will not go into that in the lecture. Just assume it's constant. And that will be simple constraint you could impose. So I'll talk about heading direction. So heading direction is maybe a little more abstract than you might first think. With the heading direction, the intuitive notion of a heading direction you might all have is actually an absolute heading relative to some reference frame in the world. For instance, when you talk about the heading of an airplane or a ship, then you're referring to the angle that your velocity vector, speed vector, has with respect to the north, estimated in some way. Or if you think of having here in a room like this as a robot that doesn't have a compass, then you might take some reference axis maybe along this wall and then compute the angle from this wall. So this is what I call a fixed world axis. It turns out, we'll look into that in detail, especially in the subsymbolic versions, we don't really need to know that world axis. That is, we don't need to calibrate it. But there's some subtle stuff going on about that is sometimes confusing. I'll gloss over that for now, but just be aware it's relative to some fixed world axis. And that's your heading. So it's not directly the, you can say it's the heading relative to the robot. The robot oriented this is 30 degrees, but you can't say, this is my heading. You see that heading would be constant. If I turn towards the thing, the heading is 0. So the heading is really relative to some fixed reference frame. Good. So what these two constraints we have on the behavior would be going to a target or going avoiding obstacles, and both of these can be expressed in terms of that variable. So for instance, if I have a target, I can now look at the target and define the heading toward the target through the angle that the direct connection from the robot to the target makes relative to that world axis. Oops. So here's this green thing is supposed to be the forward direction of the robot. And this would be the heading of the robot, and this would be the heading of the target. Yeah, so it becomes critical that we're not thinking of this angle here being the heading of the target. We're thinking of the angle to the world axis. If you're in a sailor, actually I was in the Navy, so in fact I was even a navigational staff. So I really know that from practice. And so there you would always compute all the angles relative to north. And so you would say the angle under which I see a target would be 30 degrees from north. And then what that does relative to you depends on where you're heading. So there's an important invariance here that is what you want is that the angle that characterizes the target doesn't depend on how you're oriented yourself. For instance, if you rotate the robot on the spot, the angle to the target doesn't change if you measure it this way. But if you were to measure it in robot coordinates, then that angle would change. And you'll see a little while why that would be not such a useful way to do that. Good. And very analogously, an obstacle would be characterized by the angle in the world in which it lies. And obstacles may typically be a whole range of angles. That is, you could compute perhaps how how like a minimum and a maximum heading angle that you need to steer to, that would be free, where you would be guaranteed to avoid the obstacle. In reality, the distance of the obstacle will also matter, and this will be in the way we will express the constraint. We will say that an obstacle is only important if it's close. If it's very far, it's not important. When we have these sensor-based methods, then it will be very natural because you can't really detect obstacles that are very far, but you might want to design that, how much of a distance is allowed, right? If you were too sensitive, then there would be no free direction almost all the time. So you have to have some distance dependence, but that's not really a constraint. That's more how important the constraint is. Okay, these are the constraints expressed in these variables. So the properties of these behavioral variables that are critical for what we do are again summarized here. So the variable is chosen so that it can describe the behavior. So if I have a time course of heading, then that characterizes the path, right? If you have an initial condition and you have a time course of the heading, you can actually compute the path by integrating that heading. It's inactable. Control theory is all about controllable, but that requires a lot of other things. But just intuitively speaking, it is possible to realize that heading. So for instance, the heading direction to the world, what you really would want to do is follow that time course that you generated for the heading direction. And to do that, you would have to send, let's say in these kind of vehicles, you would have to send down some signals to your motors. And these signals would be essentially sensitive to changes of heading, right? If you want to go straight, keep your heading constant, all you need to do is send the same signal to the two motors, and you go straight. And that will be controlled by that other variable speed, which I haven't really, I'm not going to go into details about. If I want to track some time course for the heading direction imposed, I might have to turn a little bit, and turning means that there's a change of heading, delta phi, and that change of heading would be brought about by sending a slightly different speed to the two motors, and I could compute, I know how large the wheels are and how wide they are on the body. It's a little geometry exercise to figure out what the relationship is between the two wheel speeds and the turning rate of the vehicle. Can be done in a straightforward way, which you do once when you design it. So in that sense, when I have that time course of desired heading directions, I can derive from that a time course of a variable that can actually be controlled. So the motors on the robot would be actually servo motors. That is, motors that have their own sensing, sometimes called shaft encoders. So they sense how much the motor has actually turned and make sure that it really turns as desired, right? So there is a control that really deals now with physical disturbances that controls the relationship between this plan of, I translate the plan of heading direction into a plan of wheel speeds, but I still have to make sure that the physical wheel speed actually is really the speed that I wanted to impose. And servo control means I'm measuring really the same variable. I can really estimate directly the wheel speed with, servo motors have a little encoder that they actually determine how quickly the shaft is rotating. For instance, they might have a simple black-white pattern on somewhere inside, and there's a photoreceptor that actually counts how many changes from black to white you have, and that tells you, digitized, tells you how much the wheel turned per second. And there are other ways to do that as well. Now, so that part of how that's controlled we'll neglect. That will sometimes not work. For instance, if the wheel slips, then make an error, right? And we'll have to see what happens then. This control matters, right? If you have a vehicle that is heavy or heavier than you load it, then it might have to generate more force to change the rotating speed of the vehicle because of inertia. And the plan doesn't really think about that here, right? The plan just says which orientation you have. And so that dealing with these physical disturbances, that will be a problem of the control, right, which we'll now neglect. The third property is that the constraints can be expressed in terms of this variable. So I just showed you how that can be done. There are desired values and undesired values. Express that. And this no calibration needed is, I'll gloss over that. We'll look at that later. This is this question of the world axis. Do we actually need to know relative to which world axis this is measured? And it will turn out we don't need that because only changes in the heading direction are important. We don't really need to know the exact value of the heading direction. Good. So that's the variable, right? And we'll just talk about heading and speed has similar properties, and we can generalize that for arms, for instance. Now, this dynamical system. So what kind of dynamical system is that? So again, we'll generate the time courses of the heading direction from a dynamical system, and that dynamical, in particular, as an attractor solution from that dynamical system. And we will build that dynamical system by adding contributions to the dynamical system. But that's where the approach is heuristic. What you can also do is you could say, I have a mathematical way of, if I have the constraints, I know the obstacles in the target, that I could now compute from some optimal principle the dynamic system that takes these constraints into account. And there is actually a solution for that for the potential field approach, which is in practice never used, by the way, because it turns out it's a very difficult computational problem. What we're doing is an ad hoc way, that is, we build it from contributions and then we assign it that it works approximately. Turns out it works extremely well, so it's not a work constraint. So I'll show you concretely, and then you will see what that means. So here's the way we express the target constraint, that we want to go to the target. So to go to the target, what we want is that our heading direction equals the heading of the target. You know, the angle that the target forms with north, and this is the angle my driving direction, forward direction, forms with north. And if they are equal, then I'm heading to the target. Right? So what I really want is that my heading direction is as close as possible to that direction of the target. In German, this is called Peilung, by the way. Peilung is the angle of a target toward north. In English, it's called bearing. The bearing of the target, right? The bearing is relative to north. So how can I do that? I built an attractor, right? You learned that last week. You built an attractor, that dynamical system that has a zero crossing. So this is the rate of change of heading against heading. That's a dynamical system for heading. Heading is the dynamical variable. You used X last week, right? Now it's phi, the heading direction. The rate of change of heading is the turning rate, right? It's just the rotational speed of the vehicle. So that's the derivative of that. And when the derivative of a state variable is a unique function of the state variable, then you have a dynamical system, right? We learned that last week. And when you have a zero crossing, you have a fixed point. So that's a constant solution of the dynamical system. And when the dynamic system has a negative slope as it goes through that fixed point, you have an attractor. Right, you learned that last week. That is, if you're to the right, you have a negative rate of change. That is next moment, it's going to decrease. So moving here left, to the left have a positive rate of change. So we'll increase your heading, you go there. And so that if I make that dynamic system, implement that on the robot, it gets as input that desired value where the target is, then it will turn over time, the heading direction will be changing toward that direction, independent of where I'm initially headed. And that will be a perfect solution. Now there is one complication is that we have an angular variable, not a linear variable. And therefore, when you're turning 360 degrees, you're back to the original variable. And so what we want is that this is actually a function that's periodic. It's a sinus or cosine function. Actually, for heading, we really want it to be periodic because even if the target is exactly in the back, we want to still be able to reach it. And so we still want to turn, right, if it's in the back. For obstacles, we'll see that when an obstacle is in the back, we don't care about it. We only care for obstacles that are in front. But for the target, if it's in the back, we want to turn around and get there. So in practice, we're using actually functions that are sinus and cosine kind of functions that have this periodicity requirement. And we'll see a little bit later that if we don't do that, that is, if we allow the dynamic system to have jumps, that always creates trouble. Mathematically, the functions are supposed to be smooth, not continuous, even differentiable. And that, if you violate that, it always ends up in trouble. You could think a jump isn't so bad if it's in the back, but in practice, there will be other contributions, and those may make that you will approach that jumping point, even though it was originally in the back, but now some obstacle pushed you around, and now you might actually sense that, and then you're going to get some real trouble, like instabilities, numerical instabilities. The system will accelerate infinitely fast and stuff like that. So I always want to make it a smooth function. That's one point I want to make. So this, we will be writing down these equations on the robot. We will numerically solve these equations on the robot, so that when we have this angle from some system that we'll have to look at, we can solve this differential equation numerically on the robot, and then generate these time courses of phi and send it to the motors, and the robot will move. For obstacle avoidance, we just use a repeller. Okay, and now this kind of idea. That is, we want to avoid that angle, and when we avoid it, it will mean that we're a little bit to the right of it. Then we will increase the heading and move further to the right. A little bit to the left of it, we decrease the heading and move further to the left. So there's some kind of a decision point, do I turn around left or right? And the decision comes from an unstable fixed point. That's the repeller. I'll talk about the range of the obstacle in a moment. There's a little bit of a cheat I often do in these lectures, in that the mathematical convention for angles is that they are positive counterclockwise. And in our papers, we did that, right? We turn to the left, in a sense, they grow these angles, right? Well, it's sort of conventional to plot these dynamic systems always with the variable to the right, right? Just also a convention. And that makes that when you're going to the right here, then the robot turns to the left. Yeah. That is a bit confusing. So in many, it's mathematically correct, but it's a little confusing to them. So I have created graphs where one of those axes is inverted. So it always is like, if you go on the right, then the robot also turns to the right. So it's not actually correct. It's just mirrored. In the data I used to make the graphs are mirrored. So just to make it easier to follow that along, right? But if you go into the papers, you will see that some of the papers, the graphs are the other way around. That's the correct way, right? So it's just like a pedagogical trick, not to have to mentally invert the direction. Good. Yeah. So what's common to these two ways of thinking is this notion of a fourth left. That is, we're contributing something, a term to the dynamical system. We'll be adding them up, actually. That's the heuristic part. We'll be add them, even though we might have to actually do something more sophisticated, but here we're just adding. And they have sort of three properties. They have the properties of having a zero crossing, which would be the attractor or repeller. The strength of those, the strength is the slope at the attractor or repeller. You learned that last week. So the relaxation time is 1 over the slope. So something strong is something that's fast, so it has a lot of influence, and that's a very steep function that makes large rate of change. So the slope is a measure of the strength. And then the range. The range is over which range of variables, values of the heading direction does that force that have non-zero contributions. So the range is actually not here from peak to peak. The range is really from 0 to 0. Some of these functions are exponential, so you actually have to, determine some criterion level when you consider the contribution to be negligible, and have some, based on criterion like that, you can talk about a range. So that range can be the whole space for target acquisition function. We will say that range is not infinite because it's a periodic variable, but it is the full range. 2 pi, because again, if you want to avoid go to a target, even if it's in the back, you'll still want to turn around. So you're not going to say, I only care about the target if it's close enough to my target. For obstacles, we will look at a more limited range and the mathematical formulas, which I don't actually have in the lectures, but you will have opportunity to do that in the exercise sheets and in papers I will give you. When you see the equations that we use to model these terms. Actually, I have some equations in the next lecture for the other case, for the non-symbolic case. So we have some talk way of how to define these ranges. We'll do that by multiplying with some Gaussian that has a width, and the width will be the range. So for obstacles, we will make sure that the range is, is reflective of the size of the obstacle. We can be more precise about that later. But, so these are the 3 parameters that we'll have. Now, where the term is, how strong it is, will be a multiplication with some factor and the range. Now, the notion that we have for how to, please.
Question of the previous slide. So there we have an attractor, right? I was wondering why the slope is going down if we are very far away from the attractor, because that would mean if, for example, we are facing the opposite direction, we would need very long to turn around, and then we suddenly turn faster.
Yes, that's true, and actually that's also not really true. These plots I just made by hand. So in reality, you're actually exactly right. In reality, the target term is a sinus function, and the sinus function doesn't have that slope goes to 0. So this is wrong. This plot is wrong. It's just I copy and paste to make these plots nice. So the actual functions we use are different for the attractor versus the repeller. The attractor is a sinus function, so the slope at the opposite end is the same as the slope here. I just used for these illustrations, I used these, I copied the same curves multiple times. The point, I should correct that. Actually, this was generic for both, I guess, yeah, but you're right here. I should have used sinus function. So in some of the papers, you will see more realistic plots. Over the years, we use slightly different functional forms for that. And there's no real, it doesn't really matter. It's more a question of mathematical convenience. The original work with Michael Dose, we used Arcus tangent, special things because of some way we could control very precisely the range. But then later we found it doesn't really matter so much. So we now use this Gaussian method because it's kind of easier. It's all for the obstacle term. So the target term is always the sinus function. Good. And so in that respect, this is also wrong. This is all just an illustration. In fact, I'm going to show the real thing in a moment. This just to make the point. So when we integrate multiple constraints, our ad hoc approach is to just add these different functions. And that's where the range will be important. And again, so that doesn't really necessarily have to be right. That is sort of another ad hoc theory. It will be, it's generally, I will have a more detailed argument why that works in the next lecture when I talk about the subsymbolic approach, where we can make it more precise why that happens. It ultimately has to do with the fact that it's only a problem about obstacle points. And the generic thing is that you will, when you violate that constraints, you will be touching a wall with one point on your robot. It would be very odd if you touch more than one point. That would be very pointy, strange kind of obstacle. And when you do that, then you can sort of see why adding is a reasonable approximation. And so here is sort of a more academic example just to illustrate the idea. So for instance, here you would have 2 target contributions. We don't usually do it that way. The targets are usually just selected at a different level, and we just steer to one target. We don't let the path planner select the target. That would be a separate issue. But just to make it easier. And let's say if you have 2 targets that are close in angle, so this here would mean that if these are really target objects, if you were positioned on top of these, you could acquire both targets, right? Because it would be, we are close enough together that the robot would be just positioned on both. Then we would want to say, well, let's fuse those and steer in the average direction of these two. So if the individual target terms are these lila curves here, and they have these attractors, the sum of these would be the red curve. Actually, here is completely the red curve. And you see that has a attractor here in the middle between those two. So that will be when you're just superposing constraints that go in the same direction. And the result of that will be some average of the same constraint of the same side, right? And if these obstacles are far from each other, then we would want the system to make a decision to go either to one target or the other. Again, for targets, we don't usually do that. But in a moment, you'll see how we do that for obstacles. Yes, please.
If I understand correctly, in the vehicle is always targeting one target, and wouldn't it be easier to that when his angle is too big, he decided to change at the one time, not change it all the time during the driving?
I will talk a little bit about that, what happens in time in a moment. Let me give you a couple of slides and I'll come back to that question. Yeah, when I say decide, it's just describing what happens. In fact, in the system, there is no separate decision system. It's actually all just emergent from this dynamics. And I'll make that more concrete in a moment. So if these two targets are just further away from each other, there's no other change here than just these lila curves here have been pushed further away along the heading direction axis. And, I made this plot so that it's nice. So you see, in this case, there is pretty much no overlap. So this is the zero crossing from this force let, which is, red now because there's a lila under that. Because the sum of here the other one is zero, right? Here the sum of the two is just one of those. And then it continues here this way. And then the other one just starts up here. And then, goes here. So in this phase, the sum is just equal to the other forcelet. And in the middle, you have these two forcelets that pull in the opposite direction, right? This one wants to pull it to the right one, rightmost target, and this one to the leftmost target, and they cancel. And so what you get is another little repeller here in the middle. This would be a repeller so that if you're heading a little bit to the right of this repeller, you're going for this target, a little bit to the left of it, going to that target. Here I'm using the strict to say to the right of, even though it is in the other image to the left. And so here you can see that now the constraints, because this was arranged to be that way, the constraints are really totally independent of each other. That is, the attractor here is at the attractor that would be valid if I had only one of those two contributions, and this one is the attractor which would be valid if I only have the other one of these contributions. So that would be the idea, that if the constraints are sufficiently separate along the behavioral axis, they will be independent of each other. And so then only one force is effective in reality. And when they're close, they're going to be averaged. That's going to be the general. In our original paper, we actually had some additional dynamics, which we called neural, where we turned on and off contributions. And that's actually also quite interesting. I don't teach it anymore because it just goes too far. It's just too complicated. But this would be the simplest way to do it. And so in this regime, the system makes a decision at some point, because you could say the unstable repeller, the unstable attractor, which is a repeller, which is this position here, that is the decision point. That is, if you're arriving at that decision, and we'll have to think about how that happens in time. You're arriving at that position with a heading that is to the right of this, you go for one. In other case, you go for the other target. It will be a decision that emerges from it. So what connects these two regimes is a bifurcation. Right? We learned that last week. Bifurcation is a property of a family of dynamical systems, right? With a parameter, and the parameter would be here the distance in angle between the two targets. So that creates a family. It's a question if you experience that, and we'll see in a moment, you can actually experience that change and really see that the angular distance between between the target changes as you move around. In angle, that's possible, right? Because when you get closer, the angle grows, right? If you're far, two obstacles that have a certain distance are close in angle, and you get closer, they can be far, right? So you would be initially moving, would be averaging, and as you get closer, you could make a decision. Yes, please.
In that way, when said, is the propeller even necessary? I mean, if we get really close to both targets, at some point they will diverge.
Yes.
With this example, one to the left and to the right, and depending on the initial conditions, to already make the decision irrespective of
Yeah.
propeller, right?
That's a good question. I was going to answer that in the context of obstacle avoidance. You could ask that same question for obstacle avoidance, right? You could ask, why turning rate 0 when you're heading to the obstacle? You know, that would mean if you're almost colliding, you have a very small turning rate, and then you accelerate. While if you're if you're this distance, you have a large turning rate. So why not make it a jump? Like have a very strong turning to the left angle and then a very strong turning to the right angle. A jump like that would be better than going through 0, right? That's maybe the question you're asking now about the analogous thing for the attractors. And the answer is that would be a very bad idea to have a jump. I was already hinting at that. You can imagine that if you're a little bit to the, let's say one way of talking about that is that for obstacle avoidance, you would have some sensory information that makes that you create that force let. And that sensory information will be variable in time, multiple measurements, your robot is wobbling around and so on. So it will not be precisely the same function. It will be noisy. And that could mean that you're a little bit to the left or a little bit to the right in different moments in time. And that will make radical changes of your turning rate. So you'll be radically turning to the left, and next moment I'm radically to the right. You can see that would be awkward, right? Would be actually the instability that's supposed to express a constraint turns into a physical instability of the robot. Would be a bad idea. And this generalizes a lot, but for an obstacle, you might think, well, it would be very special that case. I'm just heading exactly for the obstacle, but it would. There are conditions under which this will be generic, and I'll show that next lecture. What I just hinted at for targets actually is true for obstacles as well. That is, when you're far, you might have an attractor, and when you get close, it turns into a repeller. And that would be exactly a situation like that, where now you are sitting in a repeller, I mean, something that now turned into a repeller was previously an attractor, and now you need to get away from it. If you were to do it with a step function, then you would make some unstable behavior. So it creates actually undesired solutions, which can be oscillations, but also can be other kinds of solutions that are not defined by the attractors. So it's really a principle of this, that we get the decisions out of bifurcations, and that means that we have a repeller here in between, rather than some kind of logic, or some, when you have a step function, it's like fuzzy logic, where you would have some say case study. For this case, I have that equation. For that case, I have that. It's a very general theme. Those who would listen to me in the winter semester will see that that is actually a very central theme for how we think about cognition. So we, meaning a certain community, these dynamic field theory folks, seriously claim that human cognition, even language, is like that. That is, it's all just space-time continuous neural activation patterns. And they do things that look like decisions, like when I'm speaking, I'm deciding every moment in time which is word I'm going to do next, right? And that is actually concretely happening in this style, that some neural activation pattern goes from one attractor to another attractor, instabilities and so on. We're concretely modeling things like that. We're actually even modeling language that way. But it takes, of course, a lot of other things to get there. So this is the core idea here that will show up time and again during the course. Good. So I was going to say the difference between those two regimes, right? The fusion versus this decision-making regime is a bifurcation, mathematically speaking. That is, if you vary the angular distance, you have that range where there's a fused attractor. And then the instability is it turns out to be a pitchfork, in this case, a symmetrical bifurcation where the attractor splits into two attractors and leaves a repeller behind. There's always two variants, the supercritical and the subcritical. You can also have that bifurcation where the red and the blue are swapped, which is relevant for obstacle avoidance. But here for targets, it would be the classical pitchfork bifurcation, right? So we looked at this, cut through that, and cut through this here, and in between you would get that. You mathematically, if you think about what would mathematically happen if I make this continuous change, that would be exactly happening. And so what that means is, at some distance between these two targets, these 3 points, the repeller and the two attractors would just coincide. And at that moment, the slope of the dynamics is 0 right there. And that's the unstable state. And then you would be flipping into the negative slope. Right here, negative slope. Here, the slope is positive. And at that critical point, it would switch from negative to positive and it would be flat. That's what the clarification is, right? So you can go back to last week's lecture and map that onto that. And you see that is exactly the pitchfork bifurcation you had there. And I think the exercise sheet invited you to study the pitchfork, or was it the tangent? I think it was the pitchfork, right? The x to the third. I think that's on the exercise sheet. They're actually analyzing. Might have put the tangent in there. I don't remember, but I hope I did put the pitchfork in there. Good. Now, again, we're not actually using this simple one. We're using a little bit more complicated situation where the same happens for repellers. It's a bit more complicated, so I make this first example. And now we can, I think, do the same for obstacles. So here I have 3 contributions because I have a target. That's this red line. You see, now I plotted this correctly as a sinus function here. So this doesn't have that 0 slope there, the opposite end. And I have the 2 opposite contributions here, one on the left, and again, I'm cheating, so it will be actually the one on the right, but here I'm saying it is this left one here that makes a repeller, and then there's another one here that makes this other brown curve or whatever that color is that makes this repeller. And you already see something happening here. You could say a repeller forcelet makes a semi-attractor. It's not a well-defined term. You see, this is a repeller forcelet, and in a way, there's a half attractor here on the other side, right? In that, if you think of the 0 crossing as a fixed point, then there is a negative slope here. So if you're here, you're moving toward that point, and similarly on the other side, there would be something like that. That is, an obstacle pushes you away from the obstacle, and sort of where the obstacle influence wanes, that's where you will be ending up, right? So it's a sort of semi-attractor that's only attractive from one side, and the other side it goes to 0. And now, if you have that for these 2 obstacles, you see that the target term makes that into an actual attractor. So this attractor here emerges from the sort of semi-attractor that is lifted up by the target term, and they have an actual attractor here. And similarly here, an actual attractor here that comes here from this semi-attractor that's pulled down here by the target term. So in effect, under these conditions, you have 3 attractors. You have this one in the middle that's going straight through, where the 2 obstacle terms cancel. This one and that one cancel quite exactly. So the sum, which is plotted in black here, has a nice strong attractor here. And then the 2 repellers, and out there you have 2 other attractors that correspond essentially to going around this whole configuration in either this way or that way, right? Going around on the left. So you have 3 possible solutions: go straight through, go around on the left, go around on the right. This is an example I just made by hand where everything is symmetrical, right? The 2 obstacles are exactly the same curves. So that will lead to a pitchfork. So if I now move the obstacles in, I get constraint violation. That is, now I cannot move through. Here, this dotted line is imagining the robot would be at that position. See, it would be colliding, while here it would not be colliding. So if you put that through here in conflict, and so what we want is, we want to design the dynamics so that now there is a single attractor, repeller left in the middle, positive slope. And then you only have those attractors on the outside. Whereas now you can only go around it this way or that way. This repeller is gone. And so that depends on the slopes of those various things, if that's the case. And that's actually mathematically what we do in the design. We make sure that the dependence of these terms on the size of the obstacles and the size of the vehicle. We'll discuss that a little bit more next lecture when we actually really, for this sub-symbolic approach, we can do this very clearly mathematically, how we design this so that the bifurcation happens exactly at the right angular distance between the two obstacles so that it really reflects the physical constraint violation. So this change is also a pitchfork bifurcation. It's sort of the other kind where you have the repeller, the red thing, the outer branch is the repeller, and this is the attractor. So at large distance between the obstacles, you have the attractor in the middle and the two repellers on the side. And in the short distance between the obstacles, you have the single repeller left. And there are these attractors on the outside which don't go through a bifurcation. Those solutions are always there. And that is important because when you have a single repeller, you're repelled, but where do you go? Well, there's got to be something else that you go to, and that is actually this outer repeller that does that. In which one you go. So this will be the symmetrical case where everything is exactly symmetrical, looks like that. And I don't know if Lucas got so far enough to discuss that. When you break the symmetry that the pitchfork bifurcation expresses, what will happen is that you will get actually instead a tangent bifurcation. That is, the attractor and the repeller, for instance, like this one is stronger. Then what will happen that the attractor and repeller here meet, and this repeller goes through. So when they meet, they annihilate. Right? The attractor and the repeller disappear, and this one will just continuously go through. That's the same qualitative kind of layout. You have, 3 attractors initially, and then only 2 later. But it will be a slightly different mechanism. So you see that the symmetric case and the asymmetric case have the same qualitative properties. That's why it's good for the parameterization to solve this symmetric case. This you might only understand if you understand these bifurcations enough. Hopefully, the exercise helps a little bit with that. Yes, please.
But this bifurcation would only apply if the obstacles move towards each other in time.
Well, so this is design. So conceptually, I can say I want at this distance I want this behavior. At that distance, I want that behavior. So the design doesn't really have to say that I run through it in time, which might actually happen. It does happen, but it is. It's not. That's a separate step to actually experience different angular distances between obstacles in time. And the advantage, you could say, of this design is that when you've designed the different regimes to say at this system, usually you would do that like with a case discrimination. If this, then that, right? You would design that as an algorithm. And the advantage of doing it with these bifurcations is that when you now run through this in time, it will actually work. And this will happen in time. That is, it's the same thing. When you have obstacles, if it's physical obstacles, this is the distance between the symbolic and sub-symbolic approach. In the symbolic approach, we're really talking about objects in the world, the obstacles. And those, of course, have this property that if they are far, the angle between them is small. So I will tend to be at somewhere here, where I will be repelled from the average direction. If I get closer, they will move further away. And then I can figure out whether I can pass through or not, which will depends parametrically on how large they are. And that will actually happen. Now, the symbolic approach, actually, we're using the sub-symbolic approach is different because the sub-symbolic approach, you will see, it's not the physical distance between the obstacles, it's actually the distance between the sensors. And something similar will happen though. Yes.
Yeah, but what I'm meaning is,
yeah,
if I'm far away, the angular distance is very small. So it basically looks like one obstacle that
yes,
right in front of my target. And then I would already start going around and miss the point where I realize that the obstacles are in fact so far away from each other that I
Right.
could go through.
Yes, yeah, that's right. So that could happen. That is a parametric question. It could happen if the obstacles are strong enough. This is a question, the strength is also distance dependent. I didn't go into these details. So as you get closer, the obstacle contribution grows, and it depends on how strong that contribution is relative to the trajectory of the target. If the target is strong, then I might actually be pulled to the obstacles, and only as I get closer do they become strong enough to deviate me from that, and then you would actually experience that. But again, with a symbolic approach, I'm not even sure we ever had that. Actually, in the moment that it's actually difficult to do, yeah, to detect these different objects as obstacles and track them over time is actually not so easy. So to get a good demo of the defect isn't so easy. Yeah. Good. Now, let's talk about the elephant in the room. I mean, I think it already became a little. I think at least your questions have gone in that direction. So, how can this work? So I mean, first of all, it is convenient that we're designing everything in terms of the attractors, and that's actually the main advantage of our approach over the potential field approach, which I'll discuss 2 lectures down from here, because we're designing a dynamical system so that the attractor states express the constraints, right? These bifurcations are about saying they have different classes, like here, this is one solution in one, and there's another solution under different conditions, and we're designing it only for the attractor states and the repeller states for the invariant solutions, but not for all transients, right? The transients we're just assuming we're close enough to the attractors that governs the behavior. And so we don't have to design a dynamical system where all solutions satisfy the constraints. There could be transient solutions that violate the constraints, and we just have to make sure that the dynamics is fast enough so that we're always close to the attractors. And next week, I'll show you some real simulation of the sub-symbolic approach. We can actually really see that. So that's an advantage. It is actually a very difficult general problem, the problem of inverse dynamics. Lucas mentioned this as the last thing in this lecture, I believe, that if you have, given the solutions, what is the dynamical system that has the right solutions? And if you're saying, given all solutions, I want to decide the dynamical system, that's very difficult. But just given the attractors and the repellers, then you can actually have a reasonable approach. The approach is a more formal way of doing what we're doing here, which is combining normal forms. And I think Lucas mentioned this term. It's complicated by the fact that these are angular variables, so the normal forms are not the ones that you usually find in the textbook. But there are certain approaches, how to make the design where you have the attractors. Now, but why does that work? Why is it useful? And so, so that's a cool question. So how can we generate behavior that makes sense while we're sitting in an attractor? You would think then nothing interesting happens. And the answer to that is twofold. It is the nature of the behavior variable that we had, that is a clever variable. It is a speed kind of variable. And then the fact that something interesting happens comes from the environment. So let's first think about the latter. So if my robot is in a world where there is nothing, just a target, then it doesn't do anything interesting. It just goes to the attractor for heading direction, and then it goes straight to the target. If the target's fine, we'll do that. It's a question of stopping is something we've dealt with. So the complicated behavior that emerges only because the environment is complex, right? It's not because the system itself does anything complex. Now, the other question is, why can we move around while we're sitting in the tractor? Well, that's because the behavior variable is a speed. Heading direction is actually a velocity kind of variable. You could say the velocity of the vehicle is the vector, right? In 2D, the vector in which it moves. It has the angle, that's the heading direction, and the length of the vector is the speed, which I dropped here in the lecture, but which we also design, of course, and we make some simple dynamics. So for instance, you have a constant speed, then the length of the vector is always constant. So this is a velocity type variable. And when you have a velocity type variable, and you're in a fixed point of that variable, then you move, right? You move around. So for instance, if I tell you to move at 100 kilometers per hour in your car, you're moving, right? Even though it's constant, your speed is constant. You kind of follow, you just have to have steering, right, to go follow a route. And so what is actually happening is something a bit more complex. When we now combine these two things, then the attractor is only approximately an attractor, a fixed point invariant solution, because it's in velocity space, right? And then we will, as a result of that, we will move. But as a result of the movement, the angles that express the constraints, like the angle to the target and the angle to the obstacles, will change. And so it's a fixed point, but the fixed point is actually time dependent. Here's an illustration of that. For instance, here I'm using this trick of inverting the axis because it is too complex to track otherwise. So let's say initially I'm in this configuration, and I took that actually from some actual simulation, but it's from a different approach, the subsymbolic approach. So here's the target, here is the obstacle. And so I had inverted the axis, so the target is to the right of the obstacle. So the target contribution is this lila line here, and the obstacle contribution is that ochre or brown line here. And the green is the sum of those two. And you see the green has an attractor here and an attractor there, and has a repeller here in the back. So the repeller in the back is moving in the opposite direction, which is not just deciding which way to go to the target. And so one of those is essentially going around the obstacle on the right. So you would steer further to the right and go this way. That's this solution. And this one is going around it on the left. Right, it's a little bit to the left. Again, I switched the axis so the left really corresponds to left in the other direction. And the heading direction is actually closer to this solution. And so after some time, the robot has moved in a particular direction and has a particular orientation like this. And because of that movement, the bearings of these different things have changed. In fact, now the bearing of the obstacles have moved under this angle. The obstacle is to the right of the target in heading direction. And so see, this has moved to the right of that. And in fact, there is a bifurcation here that is this attractor here going around this on the right is now barely, it's just at an instability. It's just barely stable anymore. And the system is somewhere close to this attractor. And it will continue, ultimately will be, as it passes the obstacle, it will fuse with the obstacle attractor, will really approach that obstacle. And in the back, you always have that with velocity. And so there's actually a bifurcation happening right here. You'll see this term here comes down, this maximum here comes down, and it disappears. This attractor disappears, and you are sitting in an attractor, but the attractor is moving because of the sensor information change. And what you're actually doing is tracking the attractor. So moving attractor, and you're tracking it by being attracted and following it. So of course, the prerequisite for that is that your following the attractor is faster than the attractors move around. Right? If the attractors move around too fast, then you're lagging behind too much, and then constraints can become violated. And I will show you examples of that next lecture in the subsymbolic approach, where it's easier to track all those things can really happen. Yes.
The attractors and repellents, they are probably created by a distance and some other objective.
Exactly. Actually, the target acquisition often not. So we always want to go to the target, and that's a subtle thing that is. And the attractors, yes, and actually in the subsymbolic approach, I'll show you the formula, so it really falls off with distance, and that actually means that there is under change over time, rebalancing. That is, when you're far from obstacles, then the target is the dominant term. And when you're close to obstacles, then the obstacles become dominant. And that's the only chance how you can approach a target where there's some obstacles before. So you go in this general direction. And when you're close, then you're actually figuring out where there might be an opening to go around. So this time scale of relaxation, right, how quickly we go to the attractor, is sort of a design variable, right? A priori, this is just a mathematical conception, so we could just make it very fast. So we're always not close to an attractor. In practice, when you implement that, it's actually a question of computation time, and that has to do with sensory updating. So when you do this on an actual robot, you solve the equation numerically, and you use a certain step size in time how to solve the numerical equation. That is not usually a problem for your computer on the robot. We actually built a robot, which I'll show you at least a video next week, that was so cheap in terms of the computer in there, that even the computing time was a problem, that it was very slow. But if you have a little bit more money, this was 20 years ago. So now with our modern computers, that is not usually the bottleneck. The bottleneck is that you have to update your sensor information, and that takes some time. That depends on what kind of sensor you do. Sometimes physically, the sensors need some integration time. Like we had these these light dependent resistors, forgot the exact term, and they take some integration time to stabilize infrared light, or you can have just some estimation, stabilization of the estimation value of some time, and that gives you some minimum time you need between computational steps, and that means your computational steps have to be much smaller than the relaxation time, and so you can see that you cannot make these relaxation times arbitrarily small, and so that's the kind of trade-offs you have. And it's real. You as humans can avoid obstacles, but for instance, you cannot dodge a bullet, right? Because it's just too fast, right? It's the very same thing. So it's a change of the constraints that are too fast. Now, bullet is a bit extreme, but you might remember this game. I don't know if that's still played. In my childhood, we started this game where they throw a ball at you, and if it touches you, I think it's called Völkerball, like if it touches you, it's bad. I always hated that game. And there you can see, if somebody throws fast, you can't avoid it. That's essentially the functional constraint that we're talking about, right? If the changes are too fast, then a system like that might not be able to find a solution, and that's a natural limit. Yeah, so the answer to why we get, so it's useful to do this with attractors because we don't have to design the complete solution. And the limitation is, it works because if the time relations are right, we can sit in the attractor all the time, and the attractor is just changing as we move around. But we have to use a variable that is velocity-like. So there are two wrinkles of that. The potential field approach is older than ours, and I'll discuss in two lectures down, actually uses not a velocity-like, it uses a position-like variable. And therefore, it cannot actually use attractors, because then with position-like variable, when you're at a position, then you're just sitting there, right? You're not acting anymore. And that meant that they had to design all solutions rather than the attractor solutions. From the potential field point of view, our innovation was to use, these are the variables that allow us to use attractors. And you can also push it the other direction. You can actually say, oh, why don't we use an acceleration-like variable? That makes it even more mobile. And we actually did that. We built a system where the state variable was one derivative higher. And I think I'm not presenting that anymore. I used to have that lecture. Maybe I'll do that next week. I'll check. It's a little bit more complicated, but it's very agile. And we actually made someone used that for drones, someone from Brazil, when he was visiting here. And then we made a comparison of how efficient that is in some sense. I'm not sure of that. So this is very cool. So you can push this in different directions. So this is from the original work, Michael Dose was the doctoral student who did that, and at some point wrote a review article, which I was the first author on, but it's his original work in maybe also that year, I don't remember. And he actually implemented this on an actual vehicle. This was here in another building here in biology, and there we had some, this was a robot vehicle, quite large, and a lot of computing for vision. And it's very, you know, at that time, it was still a big problem to even just compute those things. So for instance, here, this is the kind of measurements we had. These little dots are measurements where the system detects obstacles. This was based on detecting everything that is not in the plane. You're comparing the image that you predict from the two cameras. If everything was in the plane to the actual images, and everything that's not in the plane is an obstacle because arising from the plane. There's to approach from that, and then see this was a case where we found this unique path to the target, which I do believe these are the obstacles here, these boxes, and there's some arbitrary place here defined as a target. It was so work that showed that the bottleneck is really that sensory information about the world, and we then developed the subsymbolic approach because we saw that even in a very simple case like that, having these estimates of physical objects that you can then track in time is quite demanding. We did things like use probabilistic methods, used neural networks for that at the time, to stabilize these estimates of an obstacle and its size and so on from these individual points we made for the neural representation of the blobs as one object, and then a set of blobs another object, estimating its width and things like that. Good. I had a whole plan here. I'm not sure it's quite realistic what I still wanted to do. So I'll close this one, this part of the lecture, and I have to decide whether I can push through the second one. Maybe I'll just do a little pass through that and give you some reading about it. Might be the best strategy. So this is we call it symbolic. So it's sense plan act-like, in the sense that we're really talking about these physical objects in the world, right? And that would mean that when you're moving, you still know where the obstacle is, and compute this updated angle, like in a map and so on. And as I was thinking, that is demanding in terms of perception. The other approach would be to use raw sensor information. I'll show you that next week. It's initially surprising that you could do that. This is the more intuitive one because we as humans think of the world in terms of objects. We're actually always interpreting everything around us in terms of objects. But for driving in particular, for these low-level behaviors, you can do a lot of things without segmenting the world into objects, and just in terms of free space. I'll show you that next week. Now, the other thing I planned here to show you is some work from Bill Warren's lab, published here in this paper, that applied these methods to human locomotion. And it was really historic this way around. That is, I had developed this approach working originally, I believe, here in Bochum with Michael Dose and some other folks, Joseph Engels, published that. And Bill Warren, who was a psychologist I had actually worked with on in other directions earlier, invited me to their lab at Brown University to teach about that, because he was just embarking on a trip to study human locomotion in a virtual reality cave. And I lectured there for a week and so on. And they actually ended up analyzing the data with these methods. And it turns out that these methods really work very well to describe the human behavior. And that's why I like to show that. So it's not, we didn't set out to model that. You see, the model actually needs some modification. But it is compatible with human behavior, which reflects probably that this basic idea that you're using attractors and that bifurcations, the instabilities, that works. And those who listen to my other course know that there is a lot of evidence in other areas for that. And this turned out to be like that too. So they did this in virtual reality to control the locomotion. Is just you walk, right? Toward a goal, avoid obstacles. If you do that in the real world, then of course you will be seeing from the start the layout, and you would adapt your walking to that. And what they wanted to do is control when you see what. So when you see the target, when you see the obstacle, under which angle you see that, and so on. They did introduce some artifacts, which actually led to a little modification in the equations. And I believe that our original equations are better for naturalistic behavior. I'm not sure I'll get to all the details, but we can do a little exercise on that. So roughly speaking, what happens is you're in this virtual world, right? It's a large cave, so you can walk. There's no real obstacle. You can walk without running into anything. And you have this thing. I was actually in that experiment, and it's really cool. It really feels amazing. So you begin to walk, and then under different conditions, so in one condition, there would be the target is just a vertical cylinder that shows up in your scene, that shows up at different distances and different angles. And then you're not turning to that. It's very trivial. It feels totally trivial. And then in another experiment, you're walking, and I think you have the target right away. I don't remember exactly. I think it's the target's right ahead, yes. And then after walking a little bit, an obstacle appears again at different angles and different distances from you. And they have to have the color, so you know which one is the obstacle and which one is the target. You can, it's also a cylinder. You can, of course, walk, it's just virtual obstacles, but you're supposed to not walk through it. And so what they then do is they just have the time course of the walking, and they can compute from that time course the heading relative to fixed axis, just in the usual way, and the rate of change, the turning rate. And so this is plotting the heading like the dynamic system. So this is the turning rate of the humans against the heading under these different conditions. The different conditions were lined up so that the target angle is always here at the center. So this subtracts the target angle. So psi minus the target angle. And then you can, well, you know, in reality, they had to turn two different directions, left and right. And you can see that there is sort of this negative slope here with an attractor at the target, right? Makes a lot of sense. Now you have, when you're further away, it isn't converging on one line, right? It's supposed to be just one line. Because the dynamic system tells you for any initial heading what your rate of change is. And they treated that by introducing some second variable there, some kind of inertial variable. But it's actually an artifact of the introduction of the target. You're walking ahead, and suddenly this target turns on. That's not something treated before that your dynamic sort of jumps from 0 to, there's a step change in your dynamics that suddenly appears. So what people actually need is to get up to speed. Right? This is the inertia. That is, if they had seen the target from the start, these lines I propose would be all lie on one curve. They wouldn't be different like that. And this is as a function of distance. So when it's very close, you have very strong turn. Right? You turn more quickly than if it's far. So there's some distance dependence empirically that we didn't actually have in our models. And for obstacle avoidance is similar. So here it's scaled so that the obstacle is here, and it's all put always on one side. So in experiment, you have it sometimes on the left, sometimes on the right. And for the analysis, they just flipped it also that you only see one side. And so what you see overall, there is here a repeller, right? A positive slope at this, and then it falls off with distance. And when the angle is very small, they have very steep turn very quickly to avoid it. And if it's a larger angle, you turn more slowly. And this is as a function of the distance. So when it's very close, you turn more quickly than if it's far. So this falling off the distance is very plausible. So again, these curves should converge onto a single curve. And the reason that they don't is possibly due to that fact that the obstacle is instantaneously switched on at a particular location. You would already be ramping up that contribution, which would mean that you initially see it at a larger distance and then it comes closer, and then the distance dependent alone would make this curve. And so, so they model this in the exact same way. So the model sort of fits the data. So the model is like our model. I hadn't shown you the equation earlier. So here, this is the mathematical form of the attractor term, and this would be the repeller term with a positive term. This is a particular way that the distance, so we use very similar, we use usually a square, but other than that, these are the distance dependence. I'll show you that next week. And this is a distance dependent I have to for the goal state. The only difference is that they used a second order equation. So they, rather than this being phi dot, they use phi 2 dot, and there's a damping term in here. And that is some kind of inertia term that makes that the system takes a little longer. And therefore, it depends on the second variable. That's how these different curves can be different. It can be, it has the second variable, the turning rate as a variable. And I give you an exercise sheet to go through. I decided if that makes sense, but I invite you to read that paper, which has a lot of other interesting aspects as well. And I'm skipping that part here. So there's something interesting in, this is the model, but I think there's also experiment here. Yeah, in experiment, they had really some cases where they have to make decisions where there's a target here and an obstacle here. So the target is at different distances. The obstacle is here. And I think it's the angular offset that is varied. And then you can really see that sometimes people go on the left and sometimes they go on the right. So they make a decision which way to go on. It depends on the angle, distance, and the distance of the target, which direction they go. And the model was actually able to predict that as well. So it's really, that model explains that decision making in this example. You don't have to understand the details of that. Okay, so I want to close by summarizing again that the main idea of the attractor dynamics approach is this idea that plans are time courses of these behavioral variables. Here it was just heading direction. Similarly, you do speed and generalize that. The time courses are generated by a dynamical system, which is structured such that the attractor solutions of the dynamic system fulfill the constraints. The constraints are expressed in terms in the dynamic system so that the attractor solution is fulfilled. And the decisions emerge from bifurcations of the attractor solutions. And